All right, so there's this idea that whether you do high intensity interval training or you do long, slow distance work, the adaptation is the same. You get more endurance. So how does this work? How do you get more endurance? And so one of the things you can look at is one of the adaptations you make is to the number of mitochondria you have. That's the process called mitochondrial biogenesis. Making new mitochondria is something that happens when we exercise train. So could this explain why we get an improvement in our endurance that's the same whether we do long, slow distance or we do high intensity exercise? So here's how the argument goes. Exercises, and I've talked to you about this, uses ATP, especially when you've got a lot of that actin-myosin interaction and your myosin head is going through the power stroke. Every time it releases from actin, it grabs a new, that needs ATP in order for that to happen, and then it's going to break the ATP when it reaches out again and cycles again. All right? When you need to go fast, you break down ATP faster. And we break it down faster than we can produce it. And this causes an increase in AMP. And we talked about that when we break down ATP, we can regenerate it from phosphocreatine or from 2 ADP molecules, one giving us 1 ATP and 1 AMP. And the interesting thing there with AMP, it activates this thing called AMP kinase. And what it is a protein, and it's an enzyme. And the enzyme activity is that it adds little phosphate. It decorates other proteins with phosphates, which are negatively charged things, which cause them to move away from positive stuff, move away from negative stuff and towards positive stuff. So when you have lots of AMP, you activate this protein, AMP kinase, and that's something that you get with high intensity exercise. You produce energy not as fast as you use it because you're going faster than you can produce it. As we talked about, you can only do that for a very short period of time. But what happens when you are using energy faster than you produce it is that you activate AMP kinase. Now, that's how you get high intensity exercise is going to activate this AMP kinase. Okay. Every time muscle contracts, one of the things that we said is that when our brain or our spinal cord sends a message, that message goes to our muscle. At the nerve, it's going to cause sodium to come in. That's going to change the charge of the membrane of the muscle from negative to positive. And that's eventually going to cause a cork in the calcium store within the muscle. And it's going to release calcium, and that calcium is going to cause muscle contraction to happen. That calcium also activates a different enzyme that's a kinase, and that's called the calcium calmodulin kinase. We're going to call it CAM kinase for calcium calmodulin. So CAM is calmodulin, so it's the calmodulin kinase. Okay, so every time we do a contraction, we increase calcium, that activates CAM kinase. And when we do that for hours, we activate CAM kinase for hours. When we do it for only a minute, we only activate it for a minute. So if we go for a long period of time, we're going to activate CAM kinase a lot. Okay. If we go for a short high intensity exercise, we're going to activate AMP kinase a lot. All right, so we've got these two different kinases now that can respond to the different types of exercise that we're doing. The interesting thing is both of them do the same thing. They increase this weird little thing called PGC1 alpha. All you have to do is think of it as PGC, okay? And all this is a special protein. And it's a protein that helps us increase the number of mitochondrial proteins. It is important for increasing enzymes for fat oxidation. It also increases the number of blood vessels that feed each muscle fiber. Wait a second, that's what we talked about as being all of the endurance adaptations. We said the endurance adaptations are to increase blood vessels in a muscle, to increase mitochondrial protein so that you can take oxygen and make more ATP, and increase the enzymes that you can use to make fat or break down fat. So now all three of those things that we say are the endurance exercise responses in a muscle, they're all caused by this one protein PGC. And PGC1 alpha is increased by both of these, AMP kinase and CAM kinase. So if we go long and slow, we activate CAM kinase, we should get PGC1 alpha. And that should give us endurance adaptation. If we go short and fast, we're going to get this big AMP kinase stimulus. Now we're going to get PGC1 alpha from that signal. So basically, if we get high intensity interval, we're going to use more ATP in a shorter period of time, resulting in a bigger increase in AMP kinase activity. If we go long and slow, we're going to result in repeated small increases in calcium. And the increase in CAM kinase is small, but it's significant. It's like 30–40%, whereas AMP kinase can be turned on, let's say, 20-fold. And really what we're looking at is it's the sum of CAM kinase and AMP kinase. These two things together are going to give us more PGC1 alpha. So if we have a little bit of CAM kinase for a long time, or a lot of AMP kinase for a short time, we're going to get more PGC1 alpha. And if we get more PGC1 alpha, we're going to get more mitochondria, capillaries, more fat oxidation enzymes. And therefore, whether you do it short and quick with AMP kinase or long and slow with CAM kinase, the result comes out the same. The only real difference is if you're in an impact sport where your body weight is hitting the ground, now you're going to have a lot more impact, so the mechanical load might be higher. So if you're doing lots of sprints and you're running on the ground, that might end up with a little bit more mechanical fatigue that could cause more damage. Whereas if you're going, if you're on a bike, sprint, really short periods of sprint, it's going to increase your endurance really well, and it's not going to make you any more risk for injury. All right, so the adaptation can be the same, and it looks like this in a picture. If you go long and slow, you get calcium. Calcium turns on CAM kinase. CAM kinase increases PGC1 alpha. If you go short and fast, you go and you break down ATP really quickly. You then combine two ADPs into ATP to drive your high-intensity exercise, and you produce AMP, which activates AMP kinase. You get PGC1 alpha. Since the two things are doing the same thing, the two proteins are doing the same thing, that it doesn't matter how you're doing it, you're always going to come down and get PGC1 alpha, and now you're going to get more mitochondria, more blood vessels, and more fat oxidation enzymes. So that means that if you want, and you have lots of time and you want to go out and cycle from here to Winters, grab a coffee, come back, or you want to go cycle up into the foothills, or you can go for hours, and that's going to give you your CAM kinase calcium signal. But if you don't have that time and you want to still get the same workout, now you can get in. You can cycle as hard as you can for 30 seconds, take a short rest, cycle as hard as you can for 30 seconds, take a short rest. Do that 5 or 6 times, same effect. Because we've done the same thing. We've activated PGC1 alpha. This is where understanding some of the molecular biology is going to make it so that you can change your training to be time efficient when you need to be time efficient, or to minimize injury risk when you have a little bit more time. But of course, this is only something you can do in young people, right? Actually, no. Look at this. This is a great study. That was a couple of years ago. And what they did is they did high-intensity interval training in old people. And what you can see is that here's young people, and here's their different genes and different signals. And what you're looking for is that you're looking for, when you do high-intensity training, what happens to the gene expression pattern. And what you can see is mitochondrial genes go up, and muscle growth genes go up a little bit, and total genes go up, and some of these things where are insulin signaling they're improving as well. But what happens in old people? Look at that. You actually get a bigger effect. You get a greater genetic effect in old people than in young people to high-intensity interval training, because it's a greater stress, and they haven't done it as much. So now your mitochondrial proteins are going through the roof. They're going up in both directions. They're going up along the x-axis, but they're also statistically significant. The significance is actually when they go up along the y-axis. So you can see in the older people, now you've got this huge stimulus for muscle mitochondrial biogenesis. You can see these genes are getting turned on more, and muscle growth even more, and muscle insulin sensitivity, those are going up as well. So, and there was no greater increase in injury rate in the old people. And the old people actually liked doing the high-intensity interval training better than they liked doing the long, slow endurance training. So you can do high-intensity interval training as long as it's body weight supported in old people. in young people, in everybody. Everybody likes, they feel invigorated when they go hard, when they sprint, when